This is the senior Kangaroo from this year, 2023. Let's just go ahead and do it then. Very first easy, nice warm-up question. Lambda to 1 means lambda here, 1 there. No, it doesn't, because lambda's less than 1, so 1 here, lambda there, which of course means with these ones on their side, this is lambda, this is lambda, this is lambda, which means 3 lambda equals 1, and lambda is 1/3. And then times it by 360, you get 120. Nice, easy warm-up question. Next one, factorize out 7 factorial from these three things, because if you take out 7 factorial from this, you just leave behind the 8, because this is essentially 8 times 7 factorial, and this is 8 times 9 times 7 factorial. So you can pull that out, and then you can calculate this, which is 81, which is super helpful, because now all I have to do is count how many 3's there are in all this. Now there are 4 3's there, there's 1 3 there, and there's 1 3 there. So I think that makes 6 3's in total. And it also leaves behind all of these numbers that don't have any 3's in them. I've halved this down to a 2, notice, and got rid of this one entirely. So now I just need to calculate this thing here, and it ends up being this, which is the answer to the question. Question 3, so if you start at 2 to the power 10, and then you add 2 to the power, what have I even done here? Okay, so this is just all the numbers from 2 to the 10 to 2 to the 18. There are a lot of them there. The next number that's divisible by 2 to the 9 is 2 to the power 10 plus 2 to the power 9. Because, like, if you're looking for, like, if you know 10 is divisible by 5, and you're looking for the next number to be divisible by 5, the least you have to do is add 5, right? That's going to be the next one. So we're going to add the number we're looking for here. That's going to be the next one. And the next one will be 2 to the power 10 plus 2 lots of 2 to the power 9. So what I'm going to ask here is how many 2 to the power 9s are there between 2 to the power 10 and 2 to the power 18? And to do that, I can find the difference between 2 to the power 18 and 2 to the power 10, and then just divide by 2 to the power 9. Again, think of an easy example in your head. Like if you're looking for them, how many multiples of 5 there are between 10 and 80. Do 80 divided by 80 minus 10 and divide by 5. That's just the exact math I've done here. Biggest takeaway, smallest, divided by the thing that you're looking for between them. If you do this, you can factorize out 2 to the power 10 here, or you can just, 2 to the power 9, and then just cancel the 2 to the power 9s, or just divide this by 2 to the power 9, divide that by 2 to the power 9, you get this. This is 5 112, which means this is 5 110, except I've missed the very first multiple of 2 to the power 9 because it's inclusive, which is this one here, just 2 to the power 10. It's just plus 0 copies of this. So I'm going to add one back in and get 511 as my answer. This is just a weird question. So 1 is less than the 7 letters that make January. 2 is less than the bunch of letters that make February, and so on. You can just do this for a while. When you get to May, things start going the other way around because 3 letters in May is less than 5, which is the month that it is. And actually, it turns out all the others don't work at all. You can count them if you want to, but these are the only months that work. There are 31 days in January. Absolute baller question this. You need to know that 2024 is a leap year. So there are 29 days in February, 31 in March, and 30 in April. Add these days up, and you get this here for answer. I just thought that was a really weird question. I don't really understand it. But anyway, a number C is defined such that n minus 6 is the second largest factor of n. So obviously the largest factor of n is just n. Now the second largest factor at most can only be half of n, right? So like even if you take a really big number, like 200, yeah, that's a really big number, isn't it? The biggest number I can think of. The largest factor is obviously 200. The second largest is 100, and you can't go bigger than that because then you're more than half the number. So if you want a number such that n minus 6 is the second largest factor, you can't go any bigger than 12, because the moment you're bigger than that, half of that number is less than n minus 6, right? So like if you go to 20, half the number 10 is less than 20 minus 6. So the largest possible is 12. 12 actually works, right? Because 6 is a factor of 12 and it's 6 less than 12. So 12 is one that works. Then you head down. 11 doesn't work because 5 isn't a factor. 10 doesn't work because 4 isn't. 9 does work because 3 is a factor and it's the second biggest factor of 9. And then 8 doesn't work because although 2 is a factor, 4 is bigger and is also a factor. And then 7 works because, of course, 1 is a factor. So we add those up, we get 28, and then we times by 11, and we get 308. Number 6, then, to do these questions, just say this first one is true and work through it. If it doesn't work, say the first one is false and work through it. So let's just say this is true. That means that the second statement is obviously false, which means at some point I need to check that it doesn't actually end up being true at the end. So, okay, true, false. 4 of these cards have false statements. Now, I don't actually know too much about that at the moment, but at the same time, I'm just going to go ahead and say that that's false. I can go back to that if I need to. Sure, I'll go back to it if I need to. The statement on card 101 is false. Well, that's false because I've said that it's true. and the statements across 102 and 104 are both false, well, that's true, which is fine because that leads there to be two trues, which makes this one false. So maybe I should have put this one at the end, but this all holds together, except it doesn't, right? Because then this thing here is made to be true now, which is a contradiction. So that doesn't actually work. So now we go back to the top and we say, okay, well, what if this was false? That means this would have to be true. So now I need to make sure there are two truths. If there are two truths, this must have to be false because there are only 5 cards. This is true because I've decided it is, and this one here is false because they're actually both true. And this, I think, does actually all hold together. It was all fine. The true statements are 102 and 104, which add to 206, and we'll have our answer. Question 7, a lovely question. You got a box X, Y, Z. If you fill it up with the box sitting like this, it goes up like maybe too high, and you get X times Y times 2 is 120, which is this. If you turn the box over to its side, so it's sitting on this base, you're going to get Y times Z times maybe 3, although it doesn't matter, it's all relative, equals 120. And then if you turn it to make like this side of the base, so you turn it frontwards, you get X times Z times 5 equals 120. It doesn't really matter how you set that up, you get this. Times all of these equations together. I think first actually divide by 2, divide by 3, divide by 5 might be the most sensible thing to do. Then times all of these together, and you get this, which is gorgeous for a couple of reasons. Firstly, I can factor out 2 10s from these two numbers here to get this. And then this is also 6 times 4, so this becomes 10 squared times 6 squared times 4 squared, which is very easy to escape the square root of because, of course, the volume of this container is just xyz, which is just the square root of this. So the square root of this is just 10 times 6 times 4, which is obviously 240 because 24 times 10. And we'll have our answer. Just a really lovely question that's going to be added to virtually all of my volume lessons, I think, from this point on. All the factors of 5 to 15. Now, 5 to the power 15 only has 5s in it, so the factors can only be made up of 5s. So you can either have factor 5 to the 0, which is 1, or 5 to the 1, which is 5, or 5 to the 2, which is 25, and so on. Those are all the factors. If we times them all together, we're just going to add up all the powers. So all this game is just a game of 0 plus 1 plus 2 plus 3 all the way to 15. You should know how to add together the consecutive natural numbers. It's just the last one times the next number, which is 16, divided by 2, which is 15 times 8, which is 120, and that'll be our answer to that question as well. Lowest prime that's 13 more than a cube, just list out the cubes, right? So 1 is cube, add 13, you don't get a prime. 8 is cube, add 13, you don't get a prime. At this point, you notice that actually, if you take an odd cube, like 3 cubed, and add 13, you get an even number, which obviously can't be prime unless you're all the way down at 2, which is not. So let's test the next even one, which is going to be 4 cubed, which is 64, add 13, you get 77, which isn't prime. Next even cube is going to be 6 cubed, which is 216, add 13 is 229. Now, you could either check that this is prime, or you could just check, because you know all the answers are 3-digit numbers, you could just check the next even cube, which is 8 cubed, which is 5112, add 13 to get 525, which obviously isn't prime. This is the last one that could possibly work, because it's the last one that gives you a 3-digit number, so therefore 229 is definitely the answer to this question, without even checking that it's prime. We've got some numbers for the smallest 4 2-digit primes. We may as well write those out immediately. Those are the 4 smallest 2-digit primes. Now, 2 of the sums are 24 and 28. So 24 is going to have to be this plus this, and 28 is going to have to be this plus this. I don't think there's any other way of doing that. So put 11 and 13 next to each other, and put 11 and 17 next to each other. Doesn't matter how you set that up, as long as it's there and there in some way. And yeah, that means 19 has to go here. I have no idea why this is a senior Kangaroo question at this point. That's 24, that's 28. This is 36 here, this is 32, this is 28, as I said. The other two sums are these two. C is the smaller one, so C is this. 5 times this plus 7 times that is legitimately the hardest part of this question. But in any case, you end up with 412. Quite an interesting question, this one. So we've got this many coins of this many amounts. If you just do 1 times 1 plus 2 times 2 plus 3 times 3 and so on, you get 55 pence. So if you make the assumption that he can combine them in some way to get all of the amounts lower than that, then the answer would just be 56 or 056. But maybe we should just try and show that that's the case. Now, he can obviously get all the amounts from 1 to 5, because he can get 1p by just having the 1p coin, 2p by having the 2p coin, 3p by having the 2 and the 1, 4 pence by having the 2 2s, and 5 pence by having the 2 2s and the 1. Now, that means I can get all the numbers from 1 to 5. Now, I can also get all the numbers from 6 to 10 because I have a bunch of 5p coins. So if I just use a 5p coin in all of these combinations, I can just do all the numbers from 6 to 10 by just doing 5 and 1, and 5 and 2, and 5 and so on. But I have 5p coins. So I may as well just do this a bunch of times and get all the numbers up to, I think up to 30 I can get by doing this system. So that's cool. I can definitely get everything up to 30. I haven't even used the 3s and the 4s. Now, if you just use all the 3 and 4s, 4 times 4 plus 3 times 3 is 25, bit of Pythagorean triple ending up in there. That means I can do 25 pence, which I already knew I could do. But if I add 1, I can do 26 pence. If I add a 2p coin, I can do 27, and so on. A 2 and a 1 get 28. A 2 and a 2, and I get 29. A 2 and a 2 and a 1, I get 30 pence. So I can, in a different way, do everything from 25 to 30. But now, notice I haven't used any of the 5p coins to get that far. So now if I just take all these combinations and add 5 pence, I'll get all the numbers from 31 to 35. And then add another 5 pence, everything from 36 to 40, and so on, adding all the 5 pence, and you can get everything up to 55. And so therefore, I can just do everything. And the only thing I can't do is 56 pence because I don't have that much money. And that'll be that done. How many positive numbers are there, or integers, sorry, whose digits do not include 0, digits sum of 6? So I started from the top. We can only use these digits. Obviously, we can't use 0 because it says so. We can't use anything bigger than 6 because then the digit sum won't be 6. We can obviously just have the number 6. We could also, these are the 2-digit numbers we could have, 15, 24, 33. Or rather, these are the combinations of these things that add to 6 when you only have 2 of them. Now, you could also flip this one and flip this one, and you'll end up with 5 things. So there's one 1-digit number and 5 2-digit numbers. What about the 3-digit numbers? Well, you can use 2 to 2, obviously. You could use 1, 2, 3. And I think you can use 1, 1, 4. And I think that's probably going to be it. Now, you could also have 6 ways of doing this, because you could do 1, 2, 3, but also you could do 3, 2, 1, and 2, 1, 3, and so on. There are 3 factorial, 6 ways of doing that one. Now, this one, there aren't 6 ways of. Here, there's only 1 way of doing, obviously. Here, you can just put the 4 at the front, in the middle, or at the end, so there are only 3 ways of doing that. So there's one 1-digit number, there's 5 2-digit numbers, there's 1, 7, 10 3-digit numbers, 4-digit numbers, and I don't have any more intelligent way of doing this other than just listing them out as carefully as possible. Hopefully you know how to do combinations of things and permutations of things like this. So the number of things is 4. There are 2 repeats of 1, which is this 2, 2 repeats of 2, which is this 2. So you get this, which is that. And then this is 4 factorial over, I guess, 3 factorial, 1 factorial, which is just 4. Or you just put the 3 here, 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 or here. Add those up, you get 10. 5-digit numbers, getting very restricted now. There are 5 ways of doing that. Just move the 2 around. And 6-digit numbers, there are only this one. Add these all up, you get 32. So the answer is 0, 3, 2. 13 then, we're going to make the picture that they want us to make. BE, which is down here somewhere on CD, is like this. And the perimeter of the triangle, which is this triangle here, is 3/4 the square. Just make the square side length 1. Very standard trick in these questions. Call this x. I should have called it lambda. I don't really know why I didn't. Now this length by Pythagoras is root 1 plus x, and this length here is 1 minus x, because this length is 1. Now the perimeter of the square is 4. 3/4 of 4 is just 3. So 3 is equal to the perimeter of this triangle here, which is 1 plus x plus root x plus 4, which is this. Move these things over, you get this. Square both sides, you get this. We are going to have to be careful of wrong solutions here, but actually it turns out there aren't any, and everything goes away very nicely. And you end up with x, which is really lambda, it should be, is 3/4. So it's 3/4 to 1, I guess. 3/4 of 960 is 720 divided by 4 times 3. And that's that done. Question 14. So the ways we can make one number the mean of the other two. Basically, a good way of thinking about arithmetic mean for 3 numbers, really for any list of numbers, but for 3 numbers in particular, is you just want a arithmetic sequence. So 135, or 159, or 1713, I think. Now I'm going to do the ones that just go consecutive first. So 135, 357, 579, 7911 first. There's a bunch of those, there's 8 of them. It's just all, because you can have this in the middle, this in the middle, this in the middle, or so on up to this. Or you can, of course, skip one and do 159 instead, and then 3711, like I said, and keep going. You end up with 6 of those. Or you can skip 2 and do 1713, and then 31115, I think. Is that right? No, 39. Oh, we're skipping 2 here, sorry. 3915. and so on. There are 4 of those. And then the last one is to skip 3 of them instead, and you get this, and you get this, and that's it. There are 2 options, except there are 6 for every single one of these things. So add those options first, and you get 20 things that work. But you could have taken, 3, 1, 5, because they don't have to be in order. 3, 1, 5. One of them is still the arithmetic mean of the other 2. So there are 3 factorial ways of doing all this, which is 6 ways of doing all this, times plus by 6. And that's the number of total things we could pull out that would make this work. Now, what's the total of all the numbers we could pull? Well, there are 10 numbers here. So it's just 10 options for the first, 9 options for the second, 8 options for the third. That's going to be 720. This divided by 720 is a sixth, which is p. And then you do 120 over a sixth, which we know is 720 because we just essentially calculated it. And we'll have the answer of 720. We have 21 marbles, some blue, red, some red. And basically, red wins or someone wins if at least one red marble is drawn. And apparently this is equal, the probability of winning is equal to the probability of losing. So that means that I changed the language here. Basically, you lose if you get 2 blues. The probability of getting 2 blues is this. You take a blue out of the total red and blues, and then you have to take another blue, and there's 1 less blue to take over the total where there's 1 less. Now that must be equal to the probability of losing. But of course, that's just 1 minus the probability of taking 2 blues. So I'm just going to write 1 minus the same thing. Now r plus b is 21, so you can simplify all this down to this. So the probability of taking your first blue is this, and the second blue is that, equal to the probability of 1 minus what you just did, because it says that the probability of losing is equal to the probability of winning. Times everything by 420, because of course you can. Add this to both sides, divide by 2. Looking for a number, times by the number beneath it to make 210. I just know that's 15. You could solve a quadratic if you want to, but it's just 15, which means r is 6. I don't know why I typed a here. R is the other one. Is 6. Anyway, you do 15 squared plus 6 squared, and you get the answer of 261. Good. I have no idea why this is question 16 in a senior Kangaroo. Legit no idea at all. There are 10 things that make actual numbers. How many things could you actually have? Well, this can be on off, this can be on off, this can be on off. So 2 times 2 times 2 times 2 times 2 times 2 times 2 is 128. It's just 10 over 128, which is 5 over 64. And then you just do 9 times 5 plus 2 times 64. Like, what even is that question? I don't understand. This question is absolutely gorgeous. Root 72 is a bit less than 9 and a bit more than 8. Now, that means 72 plus root 72 is a bit more than 80 and a bit less than 81. That means root of 72 plus root 72 is a bit more than 8 and a bit less than 9. It's less than 9 because it's less than 81. But it's definitely more than 8 because it's more than 80. It's more than 64, right? Easy. So it's definitely more than 8. It's a lot more than 8 now. Add 72, you get the same thing. Roots, you get the same thing. This number is going to be between 8 and 9, so it actually turns out to be like 8.999 something. So it's 8 point something. 8 times 50 is a 400, and you have your answer. Just a great question. Good. This question then. So the first 2 digits are always 20. Always. So essentially, we're just looking for a 2-digit number that's bigger than 25 and less than 99 that's co-prime to 20. So it can't have any factors 2, 4, 5, or 10. Although it's never going to have a 10, is it? Because, yeah. Okay, cool. So just list them all out. Now, I thought about listing them all out, and then I realized I was being really dumb. I realized I was being dumb about here, and then I just decided to run with it. And then about here, I realized, where did I realize? About here, I realized I actually couldn't be bothered anymore. It's just every number that's odd and not a multiple of 5. So you can just count. There's 4 of them in every 10, essentially. You add them up. There are 30 of them. Sure, cool, done. Question 19. This is so baller. I love this so much. Do you remember all the way back in like question 3, and you had to know that February was a leap year to not get 2024 was a leap year to not get that question wrong? In question 19, they just told you that. Absolutely incredible. So if you didn't bother looking at question 19, you might have just lost the mark on like question 3, but because you didn't realize it was a leap year. But they just told you it. Amazing, fantastic. Anyway, 29th of February 2024 is this. What's the sum of 2-digit factors? Now, this is a number theory question, so you're going to find the part factorization to this. I'm just doing bus stops in my head here. It's 2 times this, which is 2. You divide this by 2, you get this. Divide by 2 again, you get this. Divide by 2 again, you get this. Now, this doesn't divide by 2, obviously. It doesn't divide by 3 either because the digit sum isn't 3. Doesn't divide by 5. I tried 7. 7 didn't work, so I had to try 11. I just did a bus stop. It worked. It was great. I typed it again for some reason because I was so happy. Then I realized 11 worked. Try 11 again. Always try things twice. 11 didn't work. So then I tried 13. Then I tried 17. 17 worked. And 97 I just know is prime, so I could stop there. And because you've tested everything too big anyway. So this is the prime factorization. How do you get two-digit factors? Well, you just make some combination of these factors. Now, 2 to the power 4, firstly, 2 to the power 4 is 16. So 16 is a two-digit factor. You could take 11, obviously. That's obviously a two-digit factor because it's in here. But also, so is 11 times 2. And so is 11 times 4. And so is 11 times 8. So you get all those factors. So is 17. So is 17 times 2. And so is 17 times 4. And so is 97. You can't go any further than this. You can't do 11 times 17. It's too big. Can't times everything by this. It's too big. So these are all of those. You just add them together and you get this as your answer. And on to the last question, which is the classic number sort of cross question, whatever it's called. Cross number. Is it called cross number? That's it. Oh, it says right there. Cross number. Amazing. I can definitely read. Factors of 1305. So that's 3 times 21. So it's 5 times 21, which is 3 times 5 times 7. Same thing as we just did. Factors are either 3, but this is a two-digit number, so it's either 15, 21, or 35. But 4 less than that, with a two-digit number, of course, is 11, 17, and 31. Cool. 3 across is one more than a palindrome. There are way too many palindromes to list that are 3 digits, so I have to skip that. 5 is something to do with the answer, so I have to skip that. 1 down is 2 less than a square. Now, 1 down is a two-digit number. That should be easy. The squares are easy to list. 1 less than them is just all these. Sorry, 2 less than them. That looks weird. 2 less than them is all of these. But notice how the first digit of this one has to match the first digit of this one. So that can only be a 1 or a 3. So it can only be 14 or 34. But then notice 14 and 34 both end in 4s. So this is definitely a 4. And then go back to 3 across. 1 more than a palindrome. Now, if a palindrome starts with 4, it must end in 4. But if this is 1 more than a palindrome, this must end in 5. So that's great. Next, 400 less than a cube. List out the cubes. Those are the cubes. Now, you have to go a bit further than the 3-digit cubes because you're doing 400 less than them. So you have to go this far to 11 cubed. 400 less, these are irrelevant. So it's just this one, 400 less than all those 4, which are these 3 things here. 400 less than that is 600, which has zeros in it. And you're not allowed zeros, so it's just these 3. That's 2 down. Now, at this point, notice, I guess, that 1 across could either end in a 1 or a 7. So this is either a 1 or a 7. But the only one here that starts in a 1 or a 7 is 112. So this is definitely 112, and this can't be 17 here. Good. 6 less than the sum of the answers to the other 2 clues. Right. Yeah. So basically, this is a 2-digit number. So we can't be adding up any other 3-digit ones. We must be adding up 2-digit numbers to get this 2-digit number here, which is just going to be this one plus this one. I assumed that I couldn't add up these 2 without knowing what they were. So this one plus this one is either, if this is 11 and 14, is 11 plus 14 is 25, or it could be 31 and 34, which makes 65. Now, 65 minus 6 is 59, which works beautifully, which I think makes everything work here, and we're all done. The square to 5 across, 29 squared is apparently this. At this point, I can tell you I did everything in a calculator that was really boring, and I just got this. Anyway, 229 squared is 841, and that will be the entire thing done. Thanks for watching.